Up till now in statistics, what we've been doing is collecting data and performing calculations and, such as finding the median or the mean or the standard deviation of of the data that we've collected. The whole idea of it, though, is that we're doing this because we want to know the value of, or at least try to obtain the value of the parameter for the entire population. So we want to get the population mean, for example, but in most cases it's either impossible to collect data from every member of a population, or it's really not feasible to do so because the population is just too large. So what we do is we do collect a smaller sample, we get the data from that smaller sample, and we calculate the mean or what have you of that sample data. And then what we do is we take that value and we attempt to say something like, well, because our sample produced this value for the mean, we're going to say that there's a good chance that the population mean is roughly the same. But even listen to that description. I mean, we're always kind of hedging the description a bit by saying, by avoiding saying that it is exactly the value of the population mean. And that's kind of the interesting thing there, is that the sample mean that we get is a point estimate, as it's called, a point estimate of the population mean, but there's a really good chance that it's not the actual value of the population mean. Think of the central limit theorem simulation video from the previous lesson. We had a population, a sample was randomly selected from it, and then the mean of that sample was calculated. But then a second sample was selected, and its mean was calculated, and it produced a different sample mean than the first sample. And a third sample was generated, and it produced a third sample mean, and so on and so forth. And the fact of the matter is that if you have 3 or more different samples all producing different sample means, they can't all be correct. So a good chunk of what we do now in statistics, and as you go into statistics too, what will come along with that is talking about inferential statistics, and that is looking at the value that you got and saying, okay, I'm going to acknowledge it's probably not the correct value of the population parameter. So how do I account for that? How good is my result, and how reasonable of a result is it? So one simple step to doing that is to, instead of using a single value to estimate the population mean, is that we can use a range of values and say, okay, here's what I got for my sample mean. It's probably not exactly right, but it's probably pretty close. So we take our point estimate, which in this case for us is going to be the sample mean, and then we're going to construct an interval around it. We're going to take x bar as the center of our interval, and we're going to, on one side, subtract something, and on the other side, add that same thing. The product, or the thing that we're going to be adding and subtracting, is a z-score sub alpha over 2, and I will explain what that means in a few moments, times sigma sub x bar. And on the other side, the same thing, z sub alpha over 2 times sigma sub x bar. You may recognize that it's actually very similar to the formula that we use when we are converting a z-score back into an x value. It is slightly different because that formula normally would have mu plus or minus z times sigma, but in this case, we're doing it with x bar. And there's a good reason for that, which we'll get to in just a moment. But the idea here is that what we're saying is that there will be a certain level of confidence or a certain probability that the population mean will be somewhere between the left endpoint and the right endpoint of this interval. And that's our interval estimate, that there is a certain probability known as our confidence level that the population mean is within this interval. So let's start out with talking about confidence levels. We have a lot of things to unpack here. The z sub alpha over 2, the construction of the interval at different confidence levels and whatnot. So let's start with talking about confidence levels here. Now, this is based on the central limit theorem, which says that the distribution of sample means is approximately normal, where it is centered on the mean of the sample means, which actually is the population mean. And the standard deviation of the sampling distribution is the standard deviation of the population over the square root of our sample size. So, we've got a normal distribution here. And what we're going to do is talk about our confidence level. And what our confidence level is going to be is actually the area of a region under the curve that is centered on mu sub x bar. Now, it can be any size, any level of confidence we wish, and have any size interval to either side of mu sub x bar, but I'm going to pick one that comes directly off of the empirical rule because it gives us some nice values to hold on to at the moment. And I'm going to go 2 standard deviations to either side of the center of the distribution. And the idea is here that the area between these 2 red lines, based on the empirical rule, the area is approximately 0.95. This corresponds to a confidence level of 95%. So the confidence level is going to be directly tied into the area of this region. Now what that does is it produces a range of values, an interval that is centered on mu sub x bar. And what this means as far as the sampling distribution goes is that 95%, approximately, 95% of all sample means are within 2 standard deviations of mu sub x bar. But the thing to remember is that mu sub x bar is the same thing as mu, our population mean. So if we generate a sample and calculate the sample mean, there's a 95% probability that we are going to be within 2 standard deviations of the population mean. Now, everything that we've set up here is based on the idea that we know the value of mu sub x bar, that we know the value of mu. Of course, the concept of confidence intervals in general is based on the idea that you don't know the value of mu. So how do we make this adjustment? Well, it's just a matter of reversing our point of view here. Instead of saying that the sample mean we got is within 2 standard deviations of the mean, what we could say is that the population mean is within 2 standard deviations of our sample mean. So instead of an interval that is centered on mu sub x bar, we're going to take an interval of exactly the same width, 2 standard deviations to either side, but it's going to be 2 standard deviations to either side of x bar. What we've got here then is an interval here that is the same width as the interval here. It's just centered on a different point. The idea is that rather than talk about this in terms of mu, we are going to talk about in terms of x bar. So what we might say instead is that there is a 95% probability that mu is within 2 standard deviations of our sample mean that we calculated. And it's the same concept, it's talking about the distance between them. They are within 2 standard deviations of each other. It's just a matter of the point of view we're using. So the central limit theorem was based on the idea that we would actually sit there and take repeated samples over and over and over again, and through that we'd be able to figure out the value of mu sub x bar. In this case, however, we're only going to be taking one sample. And from that one sample, well, it's not possible to know the value of mu sub x bar. All we have is the value of x bar. So rather than center our interval on mu sub x bar, we're going to center it on x bar. So we're literally just going to take, we're going to use mu sub x bar and our confidence level to establish an interval that with a certain width, and then we're going to pick that interval up and put it and just center it on x bar instead. So let's take a look at how this is going to work now. So let's look at different confidence levels. So again, we're looking at a distribution of sample means here. Now, the idea is that we are going to start out with a certain confidence level. For the moment, I'm going to pick one and say 90%. Now, the way this works is that centered on mu sub x bar, we need to figure out the z-score such that the area in the middle here is equal to our confidence level of 0.90. Now, what we need is the z-score here, and that z-score is going to be the z that I mentioned earlier, z sub alpha over 2. But what is alpha, and therefore what is alpha over 2? Well, in order to find a z-score, we need to know the area. Specifically, we need to know the area to the left. All of the, whether we're using the calculator or Excel or a table of normal probability table, all of them are based on areas to the left of the z-score. So if we want to find a z-score, we need to know the area to the left. And that means we need to be able to fill in not just the area in the center here, but we also need to fill in the area of the tails. that's what alpha is. Alpha is the complement of our confidence level. The idea is alpha is if the confidence level is the probability that the population mean is within however many standard deviations of x bar, then alpha is the probability that it's not within it. Alpha is the probability that we missed, basically. Now that remaining area, that remaining 0.10 has to be split between the two tails. That's why we have alpha over 2. So if there's 90% of the area in between, then there has to be 5% in each of the two tails, so that total we have 100% of the area accounted for. So because of that, we refer to this z-score as z sub alpha over 2. Now, there is a z-score over here. It actually is the exact same z-score, but with the negative sign because, again, the normal distribution is symmetric. And if we're doing this centered on mu sub x bar, then the z-scores are the same distance to either side. So in order to find the value of z sub alpha over 2, what we need is the entire area to the left of it. And that entire area to the left includes the 0.90 and the area in the tail, 0.05. So if we need z sub alpha over 2, we're going to need to do the inverse norm command on the calculator, or the equivalent command in Excel, or again, if you're using the normal distribution tables, the normal probability tables, it's all going to be based on the idea that we're now going to have 0.95 area to the left. And again, we're working with z-scores, which means this is going to be based on the standard normal distribution, where the z-score of the mean is 0 and the z-score of the standard deviation is 1. And this will give us 1.6448, which we can round off to 1.645. So what this means is that we have a range of values here that is 1.645 standard deviations to the left of the mean and 1.645 standard deviations to the right of the mean. And the idea is then that we now would need to pick that up and move that to be centered on x bar, whatever x bar would be. Now, the reason I have a second graph down here is because I do want to play around with a different confidence level. We're going to see different confidence levels match up with different z-scores. Like on the first example I used, I started out with the idea that my z-scores were 2 standard deviations away because of the empirical rule that gave me the approximately 95% area in between. But there are all different kinds of confidence levels that we can use. Sometimes we want a very high degree of confidence, like say 99%. We want to be virtually certain that we have found the range of values where the population mean is. So a 99% confidence level means that we need to have 99% of our area in the center. And that means that the remaining 1% has to be split between our two tails. So in order to get this z-score here, we need to take the entire area to the left of it, which is the 0.99 and the 0.005 in the left tail. And that would give us 2.576 approximately. Notice here that we have a wider range of values. We have to go further out to each side of the center here, a wider interval, because we want to have a greater degree of actually, a greater probability of actually having found the interval for the, that the population mean sits in. So we need a broader interval because, well, if you want to have a higher chance, you need to cover a larger area. Think of it like fishing, if you will. A point estimate is a single fishing rod with a single hook and its bait. You gotta throw that out basically right where the fish are, and you're only gonna catch one fish. If you want to catch a bunch of fish, you use a net, and you throw out this big net, and you can encompass a whole bunch of fish inside that net at once. So the idea is that we have a better chance of grabbing the value of the population mean if we use a net, because it covers a broader area. So the higher the confidence level, the broader the area is going to have to be. We're going to need a bigger net to be more confident of catching it. All right, so let's look at an example now so we can see how all this fits together. A sample of 100 math test scores are randomly selected from a school. The sample mean test score is found to be 71. So in collecting our data and finding our sample, we find X bar to be 71. Now, the population mean, that is the mean of all of the math test scores at the school, is probably not exactly 71. But it could be pretty close to that. So we're now told to determine a 90% confidence interval for the population mean. So that tells us our confidence level. Let's jot that down. Now, the only other thing we haven't addressed here is sigma sub x bar. We're going to need that as part of the formula for our interval, but sigma sub x bar is based on two things. Sigma, which is the population standard deviation, and the square root of n. N is the sample size. So we are told the sample size here, but the only thing we don't have access to is the value of sigma until that last little statement in parentheses. Assume sigma equals 6. At the end of the video here, I will address that assumption and why it needs to be made and how we can make it. But we do need to know the value of sigma in order to be able to complete this task. So for the moment, and in most of these problems, you're going to be told to assume the value of it. So we're given the value of sigma, which is 6, and the sample size is 100. So the square root of 100 is 10, and that makes sigma sub x bar 0.6. 6 over 10 is 0.6. So we have two of the three things we need to build our interval. We need one more thing, and that is the z-score. So we've got our unknown value of mu sub x bar, but we do know that we want to have a 90% confidence level, which means an interval to either side of mu sub x bar that encompasses 0.90 of the area under the curve. Alpha then is the remaining 0.10 of area, the remaining 10% of the area. Split between the two tails gives us 0.05 as the area of each tail. And that will allow us to find the z-score that we need. So again, z sub alpha over 2 is going to come from the inverse normal command, where we need the area, the entire area to the left of the z-score we're looking for, and that is the 0.90 from the central area and the 0.05 from the left tail. Now this is going to produce a familiar value. Actually, something to realize is that the confidence level is only dependent, the z-score is only dependent on the confidence level. The sample mean does not affect the z-score, nor does sigma sub x bar, which means sigma and the sample size. None of those other three values we used up till now have any influence on the z-score, which means in a completely different problem, if I'm asked to find a 90% confidence interval, my z-score is going to be, again, 1.645. In fact, anytime you're asked to do a 90% confidence interval, the z-score will be 1.645. So that's kind of nice. The confidence level, the z-score is directly based on the confidence level and nothing else. So what we've got then is a range of values that goes 1.645 to either side of mu sub x bar. Okay, the only problem being we don't know mu sub x bar, but we do know x bar. So instead of building an interval centered on mu sub x bar, we're going to center it on x bar. Excuse me. So our interval then is going to come from x bar minus z sub alpha over 2 times sigma sub x bar, and x bar plus z sub alpha over 2 times sigma sub x bar. So x bar is 71. We found that at the beginning. Our z sub alpha over 2 is 1.645. And our sigma sub x bar is 0.6. For the right endpoint of the interval, it's going to be actually the exact same thing, but with a plus instead of a minus. 71 plus 1.645 times 0.6. Calculators are our friend here, because obviously our z-scores are going to be kind of ugly. Our sigma sub x bar is usually going to be kind of ugly too. Even if it's not ugly, it's just, it's 0.6. It's not a particularly nice thing. So what we get here is 71 minus 0.987 and 71 plus 0.987. 0.987 then is known as our margin of error. It's a way of saying, hey, we got 71, but for a 90% confidence level, we have to acknowledge that we could be off by a certain amount. And the amount that we could be off by is 0.987 in either direction. What this ends up giving us then is the value 70 70.013, and on the other side, 71.987. So what we have now is a range of values, 70.013 to 71.987. And what we're saying is that we are 90% confident that the population mean is between 70.013 and 71.987. Now, is mu actually between there? Well, unfortunately, we will never know. Unless we actually sit there and collect the data from every single member of the population and actually calculate mu, or we generate tens or hundreds of thousands of samples and build a sampling distribution. Unless we do one of those two things, we're never going to actually know the specific value of mu. But we can now say that we've narrowed it down to this range of values. And that's not bad. Now, it is based on 90% confidence level, which means it's possible that, it is possible that mu is not within that range. There's a 10% chance that mu could be smaller than 70.013 or bigger than 71.987. Now, 10% chance might not seem like that big of a deal, and perhaps it isn't. But perhaps it is. Maybe for whatever reason, we need to be more accurate than that. So we're going to do a second confidence interval for this. And we're going to do it again with a higher confidence level. Now, x bar is still 71, and sigma sub x bar is still 6 over the square root of 100. Nothing there has changed. All we're changing is the confidence level. So these are unaffected. What is affected, though, is our confidence level. And that, in turn, will affect our z-scores. Our confidence level is 0.99. That's a lot of confidence. That means that in order to be that much more confident, we're going to need a wider interval. So that accounts for 99% of the area, and then alpha has to account for the other 1%. And then that has to get split between the two tails. So our z-score then, our z sub alpha over 2, is going to be inverse norm of 0.995, comma 0, comma 1. And as we saw before, when we talked about a 99% confidence level, the z-score comes out to be 2.576. So we have a range of values that has to extend 2.576 standard deviations to either side of the mean. Well, since we don't know the population mean, we will have to center it on x bar. So x bar, again, is still 71. Our z-score, however, is larger, and that's going to cause us to extend further out to the left and further out to the right. So this time, our margin of error is a little bit bigger. To be more accurate, we need a slightly larger margin of error. In this case, our margin of error has grown to 1.5456. So it's definitely a larger margin of error, because if we want to be more confident, we have to be more willing to accept that we are off, and that means we could be off by even more than we thought. So again, this is going to result in a larger interval than before. But not significantly larger. And that's something to realize too, that with a 90% confidence level, we're between basically 70 and 72. Now we're kind of in between 69.5 and 72.5. It's not that much bigger of an interval to get more confident. And to be honest, when we're talking about a mean test score here, the difference between a mean test score of 70 or 72 as opposed to a mean test score that could go down to 69.5 or up to 72.5 is not that big of a difference. So in this case, it might be worth going to the higher confidence level. We can be more certain of our results, and really without adding on that big of a range of values there. So in a nutshell, this is how confidence levels work, or how confidence intervals work. A couple of things I do want to talk about here to wrap up the lesson. And that is, one of the things is I mentioned that the confidence level, the z-score, is directly influenced by the confidence level. And there are certain confidence levels that you see very often. Some of the most common confidence levels you see are 80%, 90%, 95%, and 99%. Now, we've already done 90 and 99 a couple of times. The z-score for 90% came out to be 1.645, and the z-score for 99% came out to be 2.576. And again, this is going to be the same for every single problem that has a 90% confidence level or a 99% confidence level, because the z-score is entirely based on the confidence level and nothing else. So it doesn't matter if in a different problem there's a different value for x bar, or a different sample size, or a different assumed value for sigma. 99% confidence interval is 99% confidence interval. So it will always give you the z-score of 2.576. 95% is another very, very common z-score that we see, and it comes out to be 1.96, the z-score for that. The z-score for an 80% confidence level, which you do see sometimes, not as often, is 1.282. Now, again, you can find a z-score for any level of confidence by doing the procedure that I showed you in the previous examples. You take the confidence level, and that's the area in between. You take the complement of it as alpha and split that between the two tails. And then you use the inverse normal command, or again, Excel or the normal distribution tables to find the z-score. And the z-scores will be different. The higher the confidence level, the larger the z-score will be. But these are four of the most common confidence levels that you come across, and they always produce the same z-scores. Now, the other thing I'd like to talk about here is the assumption of sigma. Now, going back to the central limit theorem, we saw a particular requirement that said n had to be greater than or equal to 30 in order for it to apply to any population. For smaller than that, we needed to assume the population was normal, at least for the time being. So the idea here is that I want to take a look at the formulas for S and for sigma. The formula for S, is the sum of the squared deviations over n minus 1. The formula for sigma, which is the population standard deviation, is again the sum of the squared deviations, but this time divided by n. Now, if you recall back when we first spoke of the standard deviation back in the first unit of the course, I told you at the time that the n minus 1 is there for reasons that I can't explain at this level of statistics. They aren't going to make sense. You don't know enough about statistics to understand why that difference is there, why the population standard deviation just has n, but the sample has n minus 1. I cannot explain that in a way that you would understand at this time. The important thing is that it does create a slight difference in the values of S and sigma. That difference is very noticeable when n is small. So let's suppose for a moment that the sum of the squared deviations is 100, and let's do a sample size of 3, a very small sample size. In this case, S would be equal to the square root of 100 over 3 minus 1, or the square root of 100 over 2, which is the square root of 50. And the square root of 50 is, well, it's just going to be a hair bigger than 7, 7.07. On the other hand, sigma would be the square root of 100 over 3 without that subtraction. Well, 100 over 3 is 33.3 repeating. And the square root of 33.3 repeating is 5.77. So there's a noticeable difference between the value of S and the value of sigma. However, suppose now we use a larger sample size. Let's suppose we use a sample size of 60. Well, here we would subtract 1 from the sample size, and we'd have 100 divided by 59, which is 1.69, etc. the square root of which is 1.301. We could just leave it at 1.30. On the other hand, sigma would be the square root of 100 over 60. 100 over 60 is 1.6666. And the square root of that, well, 1.666 is not that far off from 1.69. And as a result, their square roots are also not that far off. Look at the difference now. They're basically the same thing. So close as to not even matter all that much. So this is going to address how the assumption of sigma can be made. If we have large enough values of n, the difference between sigma and s is virtually non-existent. That little subtraction of 1 in the denominator doesn't make as big of a difference when n is large enough. Because it's in the denominator, because we are dividing. Dividing by 2 versus dividing by 3 actually makes a noticeable difference. But if you're already dividing among a large number of things, like 59 or 60, then that difference causes the division to produce roughly the same number, and then the square root of that is going to be even closer. So the idea is that if we have generated a sample and somewhere along the line we had enough data to calculate x bar, then we also have the data to calculate s. Now, the same way that x bar was just kind of given to us, we didn't actually have to calculate it, we also don't actually have to sit there and calculate s. It's given to us. It's given to us in the assumption of sigma. When we say assume sigma equals 6, what we're saying is, suppose the standard deviation, the sample standard deviation, was done, and it was found to be 6. And now use that same value for sigma. So the idea is that for large enough samples, and the threshold is 30, sigma is approximately the same as s. So we use the value of s as our assumed value for sigma. Now, there are times where the sample size is smaller, and then when you go into Stats 2 and talk about confidence levels more in depth, you will also talk about how to handle smaller samples and how we get away with being able to do this when we cannot say, hey, sigma and s are virtually the same. There are different ways to handle that. There is actually a different distribution, not the normal distribution, a different distribution that is used in those cases. But you'll also see that for other confidence intervals, for other statistics as well. In this course, we're only covering confidence intervals about the mean, but you can also do them for a proportion or for the standard deviation or variance. And both of those use a different distribution than the normal distribution. So when you go into Stats 2, you will learn there are other distributions out there, and they work differently, and they work with different things, but the basic concept of it is still going to be the same. Your point estimate, plus or minus a margin of error to either side, will give you a range of values with a certain level of confidence to say, okay, I didn't exactly get the value of the population parameter, but it's probably within this range of values. And that, in a nutshell, is confidence intervals.